Hello students, in this session we are going to discuss the circular motion. You might have seen objects moving in circular paths around a fixed point, right? Such as the motion of a Ferris wheel or a merry-go-round, yes? But have you ever wondered what forces are involved in keeping those objects in motion? Yes, that's what we will be discussing today. So, circular motion is a type of motion in which an object, say P, or I would say a particle P, moves in a circular path in this path around a fixed point, say O, okay? It's different from linear motion where an object moves in a straight line, right? So circular motion can be found in many places around us, from amusement park rides to the motion of planets around the sun, yes? So this is sun and this is our planet Earth. So we can also consider this as circular motion indeed. So throughout this lecture we will discuss the key terms, equations and forces involved in circular motion. We will explore some real life applications of circular motions, such as how it's used in designing roller coasters and satellites around the earth. Okay, so starting with when a particle P moves in two dimensions or in a plane such that its distance from the fixed point, say O, remains fixed, okay? Then, so we will say OP is fixed. Then its motion is called as circular motion, okay? So this fixed point is called as center. So O is our center, and the distance, this OP, which remains fixed, this we called as radius, okay? As we know, it is called the radius of the circle, or in this case we will say the radius of the circular path, okay? So when the speed of the particle performing circular motion is constant, we will say this as uniform circular motion, okay? Uniform circular motion. That is when the speed is constant. On the other hand, we would say this as non-uniform if this is variable, okay? So we will explore both of these in this chapter, uniform circular motion, non-uniform circular motion, time to time. So as I said, if the speed of the particle performing circular motion changes with respect to time, it's called as non-uniform circular motion, okay? Okay, so let's start with this basic definition of circular motion, that what we will call as angular displacement. So say that a particle is moving on this circular path, and its position, it will keep changing, right? Say this one is position P1 and this one is position P2, and here O is our fixed point. Let's use some different color. So OP1 and OP2, since these are fixed, this is radius, so OP1 or OP2, these are all constant, yes? Yes? Say a constant value, say the radius of the arc, say A. Okay. Now let's say This is the horizontal axis, say x-axis, and let's say this be theta. This is, let's say this one as theta 1 and this one as theta 2. Okay. So we will say delta theta as theta 2 minus theta 1. Okay. So as we see, the angle between the initial and final position. So what was its initial position? It was at theta 1, right? The particle initially, say it was at P1 position. So initially its angle with respect to the x-axis was theta 1. And then the particle moves and came here at P2 position. It makes an angle theta 2 with respect to the x-axis. Yes? So we will say the angle between the initial position and the final positions of the particle in a given interval of time. Definitely you should mention this, that in a given interval of time, because the particle is moving. So in this given interval of time, the difference between this position, initial and final position, we call this as angular displacement. This is the angular displacement of the particle. Okay? So we will write this as P1 O P2 delta theta, and this is the angular displacement of the particle. Okay? You can show this, or it is not so difficult to prove, that we know from the concept of coordinate geometry that if the displacement is small, then you can write this as delta S equals R delta theta, where delta S is the length of this arc. Okay, so you know that length of arc mentioned in this symbol. So this is our delta S. So you can prove this, that delta S equals R times delta theta, or I would say, if you take more, I mean this is a very crude way of saying such things, that delta S equals R delta theta. Okay, basically you can write this as delta S approximately R delta theta. But in the sake of computations, and we will assume this as very small, it is very small. So in that sense, we can safely write this as, these equations hold. No need to write this symbol, almost equal. It is equal. You can assume if this quantity and this quantity is very small. On top of that, this hold, in this case, this quantity, the unit will be in radian. Okay, it is not in degree. It is only true in radian. When the angle is in radian, only then it is true, not in degree or not in some other unit. Now, as I mentioned, since the particle is moving along this circular path, so given any time, its position will change, right? Say at t1 times, the particle was at position p1, and at t2 times, the particle at position p2. Say in some t3 times, the particle will be at p3 position. So in this way, since the particle is moving, so at different times, its positions will also get changed. Yes? What is the underlying meaning? What I am trying to convey is this, right? So the positions of the particle will change with respect to the time. Correct? So similarly, theta 1, theta 2, theta 3, this will also get changed. Yes? Angular displacement, angular positions of the particle, everything will get changed. So in this connection, you can say that we will have some velocity of the particle because its position is changing. And as we know, the velocity is nothing but changing of positions of a particle, right? So we will measure the angular velocity of a particle. Angular velocity as changes in its angular displacement. Okay? Delta theta by delta t. Or you can write this in this way. Say a particle moves from P1 to P2 position. So in this changing of position, what was its angular velocity? Now in this case, if I say angular velocity, it is a very crude way of saying, we would say it as average angular velocity is theta 2 minus theta 1 upon t2 minus t1. If the particle moves from position P1 to P3. Let's say this one as P3 position, it comes here, okay. And let's say this as it makes an angle theta 3 with respect to the horizontal axis, x-axis. So in this case, we will say the average angular velocity of the particle is theta 3 minus theta 1 upon T3 minus T1 in this arc, along this arc, okay. Similarly here, along this arc, you have to mention this. So the average angular velocity along this arc is this one. Average angular velocity along this arc is this one. But this is average. And if we want to compute instantaneous velocity, there are, as we have seen in our earlier classes on mechanics, that we have two types of velocity. Yes, average velocity and instantaneous velocity. So average velocity is computed in this formula, and we can also compute instantaneous velocity with the help of calculus. And so for that, what we are going to do is, we are going to take limit, okay. So instantaneous angular velocity, it will be the limiting value of this ratio, okay, which we mention as d theta dt. Okay, so say you have given this question that what is the instantaneous velocity of the particle at P2 position. Whenever we will say average velocity, we will mention along this arc. We will not say any point, we will not mention any point. But instantaneous velocity is, the concept of instantaneous velocity is computed at the point, at a given point. Say what is the instantaneous velocity at P2 position. We will compute this in this way. Limit T1 tends to T2 from here. Yes, it will be here. From this ratio. Theta 2 minus theta 1 by T2 minus T1. This is the limiting velocity at P2 position. Limiting angular velocity at P2 positions of this particle. But the average velocity, whenever we are saying average velocity, then we are mentioning this arc, along this arc. It is not a point concept, it is an arc concept. And whenever we are saying limiting velocity, instantaneous velocity, it is a point concept. This is measured at P2 point, okay. Okay, so in this way we compute the angular velocity, either average or instantaneous velocity of the particle. And we mention this angular velocity as omega, okay. This is called omega. This is not W. This is Greek alphabet, small alphabet, omega. So, in case of uniform circular motion, we have our omega is omega A. Okay? We do not need to compute the instantaneous velocity separately. It would remain same, because at every point the velocity is same. Yes, because the particle is in uniform circular motion, so its speed is constant, speed is not changing. But when the speed will change, at that time we need to figure out this one, okay, instantaneous velocity, because speed is changing. Okay, now I would give you some key points here that you should remember this thing, that average angular velocity this is a scalar quantity, okay. On the other hand, instantaneous angular velocity this is a vector quantity, okay. Now this is a very important point, and you may think that why I am saying such things. Well, first of all, I am not saying such things. You can prove this mathematically, that average angular velocity is a scalar quantity. It is because this average angular velocity does not obey the vector law of addition. Okay, you can prove this. You just try this in your as an home assignment, that average angular velocity does not obey the vector addition rule. Okay, therefore we do not grant this as a vector quantity. Okay, so this is the reason behind to not grant this as a vector quantity. Another important point I just want to write here, that if a particle makes in rotation in t0 seconds, say, okay, then average angular velocity is given by this formula, 2 pi m upon t0 radian per second. Okay, this is radian. Okay. So say a particle is moving in a circular path. Therefore, if it's cover 2 pi distance, then it means that it finishes a complete revolution, right? Because the circumference or the length of the circular path of a unit radius is 2 pi, right? Now, if it makes n revolutions or n rotations, it means it covers 2n pi displacement, right? It covers 2n pi distance, right? Now, if it makes n rotations in t0 second, therefore the average angular velocity will be this 2n pi by t0, and since it makes uniform, since we assume that the velocity is uniform, therefore the average angular velocity is given by these equations, right? 2n pi by t0, yes, very simple. Let's say if t is the time period, then t is, the definition of t is given by 2 pi by omega. We will say the time period in this way. Time period is defined by these equations. And we will say the f as frequency of the uniform circular motion we will define it as the inverse of the time period 1 by t. So I am saying this, I am writing these expressions, better you should also write it down in your copy and box it in this way, because we are going to use this in solving problems, okay, numerical problems. F equals 1 by t. So let me use different color. This one will be red and the box will be black. So you also write it in your copy and make it in box, because we are going to use this in solving numerical problems. So what is our t? T is our time period defined in this way. What is our f? F is the frequency of the uniform circular motion defined as the inverse of t. Okay. And from these two equations, let's mention this as 1 and this as 2. We can show that W is 2 pi f, right? Yes. Now we will discuss about the relation between angular velocity and linear velocity. Let's go to another page. So, relationship between angular velocity and linear velocity. Now we know about linear velocity, right? We have seen that linear velocity, if s is denoted as displacement of a particle and v is the velocity, we know that v equals ds dt, right? Yes? So what is the relationship between angular velocity and linear velocity, and we will derive this relationship between them using this formula as what I have mentioned in beginning today, that delta S can be written as R delta theta if the displacement is infinite small or very small. Okay, it is delta S, it is delta theta. Then we can write that, and this is R, that delta S can be written as R times delta theta. Now what we are going to do, we will divide both sides by delta t, and since R is constant, we obtain this thing, right? Now we know that delta theta upon delta t is average angular velocity, right? But we are interested in instantaneous velocity, therefore taking limit to both sides. This gives V equals R omega, right? This is instantaneous angular velocity is defined as omega. So the relationship between linear velocity and angular velocity is given by this thing, okay? V equals R omega. So in this context, I just want to mention one more thing here, that since these are vector quantity, angular velocity, linear velocity, so definitely they have some direction, right? So the direction of linear velocity is along tangent, okay? So if V is the velocity of the, the linear velocity of the particle, then its direction is the tangent at this point, okay? Similarly, if, let me use different color. Similarly, if a particle, let's say a particle is moving in this direction, so clearly this is the direction of linear velocity tangentially, and the direction of the angular velocity, that is omega, is given by right hand thumb rule, okay? So if the particle is moving anti-clockwise direction, then the direction of the angular velocity would be along the outward of this paper, okay? But if it's moving along the clockwise direction, that is in this direction, then the direction of the angular velocity, that is omega, would be inward of this paper, okay? This is an important relationship when we are going to solve some problem, and also in our upcoming lessons, this relation is required to derive some more interesting equations, okay? So next we will talk about acceleration. Since velocity is there and velocity is not constant, therefore acceleration will definitely occur, right? So you know, in the circular motion there has two accelerations, okay? So the first one is angular acceleration, and the second one is linear acceleration, okay? So as you can see from the name itself, you can get the feeling, right? Angular acceleration, linear acceleration, angular velocity, linear velocity. So everything in the circular motion, you will find two types of motion terms, right? Like linear displacement, angular displacement. Linear displacement is along the arc, angular displacement is along the angle. Linear velocity, angular velocity. Linear velocity is along the arc, again along the arc, because it is defined in this way. And then angular velocity is along the angle again, because it is defined in this way. Similarly, angular acceleration, linear acceleration. Okay, so what is the definition of angular acceleration? Well, we define angular acceleration in this way. Alpha, let me use red color. Alpha is d2 theta dt2. That is derivative of the velocity, right? ddt of d theta dt. Yes. Now one thing I just want to mention here, that angular acceleration will be 0 if angular velocity is constant, right? If d theta dt is constant, then definitely ddt of constant is 0. Yes. But on the other hand, linear speed of the particle may or may not be constant, but direction of linear velocity continuously keeps on changing, right? So velocity is continuously changing, yes? Therefore, acceleration, I mean linear acceleration cannot be zero. Angular acceleration can be zero, but linear acceleration cannot be zero. And we can resolve the linear combination further into two more components, okay? Tangential acceleration, this is denoted as AT, and radial acceleration, okay, which is a very important concept, and we will be doing lots of problems on this. It is known as radial acceleration or centripetal acceleration, okay. It is denoted as AR. Let me just write down the name here, some different color. Yeah. So this is tangential acceleration, and this is radial acceleration or centripetal acceleration. Okay, so the thing is something like this. So this is the linear acceleration, let's say, and we have resolved it into two further components from parallelogram theorem. We can resolve this a vector into two components, right? So let's say this is our AT and this is our AR, okay. So this AT, this is, you can see from the name, it is along the tangent, okay. The direction of AT is along the tangent vector, okay. And the direction of AR is, it is along to the center, okay. So this is, so for that reason it is called as radial acceleration. So in a circular path, let's say a particle is moving, the direction along the radius, centripetal acceleration along in this direction, and tangential acceleration acts along this direction. I am assuming that particle is moving anti-clockwise direction, okay. So this is very important concept, okay. I just want to add here one more thing is that if speed of the particle is constant, that is, as I mentioned, if v is constant, then at will be 0, correct? Because at is dependent on v. Now there is also a relationship between at and ar, as we know that at equals dv dt from the definition tangential acceleration. So this v you can write in this way, right? We know v equals r omega. Therefore this is r, since r is constant, this is r d omega dt. We can write this alpha. D omega dt is our alpha. Therefore, sorry, it will be at equals r alpha, okay. Next I will briefly talk about centripetal acceleration. So it is responsible for change in direction of linear velocity, okay. This component can never be 0, okay. Remember these two things. It is responsible for change in direction of linear velocity, and this cannot be 0. As, can you tell me why? Because the direction is continuously keeps on changing, right? Since the particle is moving in a circular motion, and centripetal acceleration is responsible for change in direction of linear velocity, since the particle is continuously moving, its direction is continuously changing, right? So it cannot be 0, correct? So the value of AR is given by this relationship. AR is V square by R. Maybe in some session we are going to prove this, that how this relationship has appeared. But for the time being, you just remember this. You can also write this as in this way. We know V equals R omega, therefore R square omega square, substituting the value of V, we obtain R omega square. Therefore, AR is omega square R. So this is another relationship between the centripetal acceleration and angular velocity and R. So centripetal acceleration and tangential acceleration, AT, clearly these two are perpendicular to each other, right? Yes, we can write this, that the net linear acceleration A in this way, A net as A t square plus A r square. Okay, that is dv dt square plus v square by r square or r omega square, whatever, and its angle, okay, tan theta is given by AR by AT. This implies theta equals tan inverse AR by AT. Okay? Okay, so let me just briefly note it down that what are the formula and relationship, and or you can say equations we have derived, okay, since these are all required to solve numerical problems. Angular velocity omega equals d theta dt. Okay, we have learned this relationship. Linear velocity v equals ds dt. We have learned relationship between v and omega is v equals r omega. Yes, we have learned angular acceleration alpha equals d omega dt. We have learned tangential acceleration, and the relationship between angular acceleration is this, and AR, that is centripetal acceleration, is omega square r. So these are the most important ones that are required to solve numerical problems. Okay, so you just note it down in your copy in the left hand side as a formula, because this will be required. Given a particle moves in a circle of radius 0.5 meter at a speed that uniformly increases, find the angular acceleration of particle if its speed changes from this to this in 4 seconds. Okay, so we have to determine the angular acceleration of the particle, right? That is alpha. Yes, and the data has given to us is its speed is changing from 2 meter second to 4 meter second in 4 seconds. That is, acceleration was given, right? dvdt is given, right? We can compute dvdt. dvdt is not given directly, but we can compute it. How we can compute? So it changes, since the speed is changes from 2 to 4, therefore v2 minus v1 upon t2 minus t1. This is 4 minus 2 upon 4. Yes, this gives us 2 by 4 equals half. So we obtain our AT, right? Our AT is half, correct? And we know the relationship between AT and alpha. Yes, AT equals R alpha. And from the question, we have to determine alpha, right? And R is also given. R is 0.5, implies we know. I am not writing subjectively. I am just solving the problems by giving the formula, so that you can understand that how to apply those formulas, that what we have learned. Okay, so whenever you will solve the problems in exam, or if you are writing on your notebook, then write it in a subjective proper manner, okay, so that you can understand it later. I am doing this right now because I have to solve lots of problems, so that you can grasp the knowledge quickly by going through this lecture session. But whenever you will write it, you should write it subjectively, neat and clean manner, so that you can understand. Especially this will be helpful when you will be preparing for yourself for exam purpose. Okay, so we have evaluated AT, which is half, and here R is half times alpha. This gives us alpha equals 1. Therefore, the angular acceleration is 1 radian per second. Okay, alpha equals, yes, sorry, it would be second square because it is acceleration. Okay, given the speed of a particle moving in a circle of radius r equals 2 meter varies with time as v equals t square, where t is in second and v is in meter per second. So find the radial, tangential and net acceleration at t equals 2 seconds. So here we have to determine the radial, that is AR, and the tangential, that is AT. Also the net acceleration. Yes, we know A net is AT square plus AR square, right? So once we determine AR and AT, A net will follow automatically. Yes. So what is our AT? Yes, try it yourself. Don't follow my session entirely. Try it. It is very easy. See, AT we know dvdt, and V is given is t square. Therefore, ddt of t square, and as since it is an instantaneous velocity, so we need some particular position, and the position is at t equals 2. Therefore, t equals 2. So ddt of t square is 2t. T equals 2. This gives us 4. Yes. So we obtain our AT equals 4. Okay. And once we obtain AT, we have to determine our AR. How we will determine our AR? AR is determined by V square by R. Okay. We obtain our V is T square. So T square by R. Our R is 2 meter, right? And this is at t equals 2 point. So this gives us 2 square upon 2. This is 2 to the power 4 by 2. This is 2 cube. So we obtain our AR as 8. Okay. See, we obtain AT, we obtain AR. It is so simple, right? We just apply the formula. That's all. There is nothing, so no tricks, no extra anything. Just simply formula. That's all. So we have to just remember those formula, and the problem will be solved. Okay. So now we can easily determine our A net, substituting the value here. I am using different color. This is our AT square. AT square is 4 and AR square is 8. 8 square, solving 16 plus 64, that is 4 root 5. Okay. So our AT is 4 meter per second square, that is tangential acceleration. Our AR is 8 meter per second square, that is centripetal acceleration, or you can say radial acceleration. And our net acceleration A is 4 root 5 meter per second square. Yes. Given an aircraft executes a horizontal loop of radius 1 kilometer with the speed of 900 km per hour, then the ratio of its centripetal acceleration and the acceleration due to the gravity will be. Let us first feel that what is the problem given. Okay, we will definitely work out the problem, but let us first imagine that what is happening in the background. Given this aircraft executes a horizontal loop. So do you know what does it mean by horizontal loop? This phrase is very confusing, isn't it, sir? Horizontal loop. Yes, actually this loop, horizontal is easy to understand, but what is this loop? Well, this loop has two different meaning in English dictionary. Okay, if you are in computer science, then the loop has different meaning, but in this case loop has some other meaning. Okay, so basically what does loop actually mean? I mean, if you tell someone who is very nerdy computer type guy, towards him or her it is something run continuously. It is some sort of series of instructions that is repeated until a particular thing happens. Okay, so you give your code a loop, so it will run continuously until some particular instruction that was given, it happens. But in this case, this is not this series of instruction. Okay, in this case it has some different meaning. So that another meaning which is applicable here is loop is a turning, or you can say a vertical circle, okay, which is made by especially an aircraft in the sky. So something like this which is applicable here. So when an aircraft in the sky make this vertical circle, we call it as a loop. Now here it is in the horizontal, So it is not a vertical, it is a horizontal loop. So it has made this horizontal circle in the sky. So here is the aircraft. So basically it boils down to the circle problems, I mean the circular motion problem as what we are doing today now. So nothing so difficult, only this loop is some sort of confusing. Rests are crystal clear, I hope so. Okay, so let us now solve this problem. So let's draw this circle and let's assume P is our aircraft and the radius is given as 1 kilometer. Okay, so let's say O is the center. So the radius, say R, small r, is 1 kilometer. This gives equals 1000 meter. Okay, I am converting this into meter because we need in SI system, everything should be converted in SI system. Okay. And the speed of the aircraft, that is V, is given as 900 kilometer per hour, which if we convert into meter per second multiplying by 5 by 18 meter per second, this gives us 250 meter per second. So we have V, we have R, we have to calculate the centripetal acceleration, that is AR. Radius acceleration, we know this as V square by R. See, everything now boils down to simple to the formula, nothing so difficult. So if we simplify this now, this is 250 square is 62500 and we have 1000. So this is 62.5 meter per second square. Okay. So we obtain our AR and acceleration due to gravity. Acceleration due to gravity is 9.8. So AR by G is 62.5 by 9.8. If we solve this, it is 6.38, which is approximately 6. So the correct answer is 6. Okay. Given a point moves along a circle with a speed v equals kt, where k is some constant, we have to find the total acceleration of the point at the moment when it has covered the nth fraction of the circle after the beginning of motion, where n equals this quantity. Okay, so let us first write down the data what is given in our hand. We have given that v equals kt, and the value of k is given 0.5 meter per second square. We have to determine the total acceleration of the point, that is a net, at the moment when it has covered the nth fraction of the circle. So nth fraction of the circle means the circumference of the circle, right? Let's say the point or the particle start from here. Let's say this is the nth length of the circumference, or you can say this arc length. Let's mention this as AB. So AB equals 2n pi r, right? Because it is the nth part of the total arc, and we know the total arc length, that is the circumference of a circle. Since the radius is not given, we assume it as r. So the circumference, we know it is 2 pi r, yes, assuming r is the radius of the circle. So the nth length of the circumference is 2 pi nr, yes. We have to determine a net, that is this quantity, at square plus ar square. So we have to evaluate at and ar separately, and after that we have to substitute the value inside the square root, and then we are finished, yes. So since we have to deal with the arc length, that is s, yes, so let's convert this equation into s. We know v is ds dt equals kt implies ds kt dt. It is just simple calculus. Assuming start from 0, yes, s equals 0, and say this s equal s. So this is s, and we know here the value s is actually 2n pi r, right? We will substitute those later. T equals 0, and here t equals t, kt, dt. We will not do this calculation here. We will substitute later the value. We have t square equals 2s by k. Yes? So we obtain one relation, t square equal 2s by k. Yes? Okay, so now what we are going to do, let's put a box here so that things don't get jumbled. So we have to determine AT and AR. We know our AT is divinity, yes, and divinity is K because V equals KT. So we obtain AT and we have to obtain AR, and AR is V square by R. So V is KT, K square T square by R. Substituting the value of T square from here, we have K square times 2S by KR. Yes, this is K times 2S by R. One K will get cancelled out. So now we will substitute the value of S. We have our S is this, right? 2n pi R. Therefore, K times 2 times 2n pi R. This is the value of S. Yes. If you have any doubts in understanding, do let me know, okay, in the comment section. So this R and R will get cancelled out. So it is 4n pi K. We can now put the value of K also. K is given as half. So 4K is 2. So it is 2n pi, and here we have half. Okay. Okay. So now let's substitute here. This is equals AT is half. AR is 2n pi, that is 4n square pi square. Okay. If we simplify this, this is 0.25. Now 4 by 100 times pi square. Yes, because n is 1 by 10. So we will now just do some simplification in the calculator, and I will directly substitute the value. Definitely we will get some approximation because pi is a irrational number. So the approximate value will be something like this: square root of 0.644, which is 0.8. Okay, so approximately the value is 0.8 meter per second square. Yes, given a stone tied to the end of a string 80 centimeter long is whirled in a horizontal circle with a constant speed. If the stone makes 14 revolutions in 25 seconds, what is the magnitude and direction of acceleration of the stone? So let's write down the data first. What we have in our hand. The length of the string is 80 centimeter, that is the radius of the circle is 80 centimeter. We can say this as 0.8 meter because the data are all answer. The answers are all in SI, so we convert this into SI system. Okay. Now what next is given? The speed is constant. Okay. Apart from that, the stone makes 14 revolutions in 25 seconds. So the frequency is 14 by 25, right? Because it has revolved the complete circle 14 times in the duration of 25 seconds. So the frequency is 14 by 25. On the other hand, we also have seen that frequency is given by this expression, yes, because frequency is basically inverse of time period and time period is 2 pi by omega. So this is omega by 2 pi. So it will be inverse of this. Okay. So omega by 2 pi. So from here we obtain omega as 2 pi of f. So from here we can evaluate omega. Yes. 2 pi times 14 by 25. This gives 20 pi by 25. Okay. So we obtain omega. We have L. And from here we can determine our AR, that is the magnitude of the acceleration. Since speed is constant, therefore AT equals 0. Okay, so now we have our AR is V square by R, but we are not going to use this here because it is redundant here. We do not know V, but we know omega, therefore it is omega square R. Substituting the value of omega, 20 pi by 25 square. See, so simple, isn't it so? You just have to substitute the formula, that's all. Times 0.8. If we simplify this, since pi is involved, therefore some approximation will come. Let's see. It will be around 9.91 meter per second square. Therefore, C is the correct choice, and since AR, as we know, it is centripetal acceleration, so it definitely works along the direction, therefore along the radius. Yes? If you have any doubts, do let me know, okay? But I think these are quite simple problem. You just have to apply the formula, that's all. And for that you need practice and practice and practice. It's simple, yes? Given a car is moving along a circular path of radius 500 meter with a speed of 30 meter per second. If at some instant its speed increases at the rate of 2 meter per second, then at that instant the magnitude of the resultant acceleration. Try this by yourself, okay? Don't follow my session entirely. You try this, only then you can learn. Pause the video, try it yourself, okay? Meanwhile, I am solving this problem, and if you have any doubts, then you again see what I am doing. So, since we have to determine the magnitude of the resultant accelerations, and in this case our AT is not constant, yes, because speed suddenly increase. So, A net. So, let us first write down the data, what we have in our hand. We have the radius, R is 500 meter. We have the speed, that is V, is 30 meter per second, and the tangential acceleration, because the speed increases at the rate, it means AT is 2 meter per second square, yes? So we have AT, we just have to determine AR. Very simple, this V square by R. We have V 30 square, R 500. See, once you note down the data, solving the problem is so easy. This gives 9 by 5. Now we just have to substitute the same thing I am doing again and again. Once you become expert, while practice and practice, then you will see every problem is trivial. There is nothing so difficult. We have 2 square, 9 square by 5 square. If we now simplify this, this is 4, this is, I have to calculate it. This is 3.24, 7.24, approximate value. It is almost 2.7 meter per second square. Yay! So now we will discuss about motion in a vertical circle. Okay, so let's say we have a circle here. Assume this as a circle. Okay, I am drawing this with my hand without any compass. So let's assume we have a circle, and this is a fixed point O. Let me use some other color, and P is any object here, or you can say a particle. Okay, in physics we will emphasize more on particle instead of saying it as an object. Okay, so that's why it is called particle physics. And OP, it is an inextensible string. Okay, what does it mean by inextensible string? It is not an elastic string. Okay, and it is also very light. I mean, we will neglect the mass of OP. So in that sense, you can also say it is also a light string. Okay, inextensible light string, so that its mass is negligible. Okay, and length of OP, say it is R. Okay, so a particle P is attached with the string, and it is being rotating this circle vertically. Okay, so we will now discuss the motion of this particle along this vertical circle. Okay, so first let us draw the free body diagram of this particle here. So we have the mg. One more thing I forgot to mention, we assume the mass of the particle as m. Therefore its weight equals mg. Yes, so now we are going to draw the free body diagram of the particle. We have mg acting downwards, and this is the horizontal component, and the normal, that is the vertical component. So if this angle is theta, I am just drawing the free body diagram, that's all. This is theta, then this is also theta, right? So this one is mg cosine theta, and this one is mg sine theta. Yes, okay. So this is the free body diagram of a particle at any point P moving in a vertical circle. Now these are all initial conditions, right? That OP would be an inextensible light string, the length of the string is R, and the mass of the particle is m, therefore weight is mg. So since the particle is moving along this direction, along anticlockwise direction, therefore an initial velocity is also required, right? So we assume the initial velocity of the particle as u. Okay, since the particle is moving along this direction, therefore the initial velocity at the lowest point A, let me use some different color, along this direction. Okay, so let us now discuss the motion of the particle in this vertical circle. Let us now determine the height of the particle at position P from the lowest point, that is from the ground. Okay, height of the particle at P from the ground. Let's say this as h. We will first determine h because it is required. So let me just draw this circle again once here. I am just drawing the semicircle because this is enough for determining h. Yes. So this is our O, this is our A, this is our P. So we need to determine the height, right? That is this quantity, yes? If we say this as A dash, so H is equal A dash P, right? So how we can determine this? It is very simple. So because this height is this height, yes, and we know this angle is theta, we know this is R, we also know this is also R. So if this is P dash, therefore A dash P is AP dash, right? So how much is AP dash? It is R minus R cosine theta, right? Because R and this one is R and R cosine theta. Yes? Because this is a right angle triangle. So we obtain our H as H, therefore H R 1 minus cosine theta. Yes? Okay. So now what we are going to do, we will apply the energy conservation principle at point P. Yes, because there are no external forces, I mean disturbing forces like friction and all those kind of stuff. Therefore we can easily apply this conservation of mechanical energy. So from the principle of conservation of mechanical energy, we can say that potential energy, I mean mechanical energy, and at this point at P would be equal to mechanical energy at point A, right? That is potential energy plus kinetic energy at point A equals potential energy plus kinetic energy at point P. Yes? So substituting the value, we have at position A, since it is the lowest point, therefore height would be 0, right? 0 plus the kinetic energy, since an initial velocity has been given along this direction. So kinetic energy at this point is half mu square. Yes. Now potential energy at point P, how much it is? It is mgh. Yes. As I mentioned, we required h. And kinetic energy at this point, it is half mv square. Yes. Now we have to simplify this. It is u square equals 2gh plus v square. Yes. So you obtain u square equals 2gh plus v square. This implies v square is u square minus 2gh. Yes. Let us box this relationship because this is important. And we also know h, right? We will not substitute the value of h here. And let us box this one also because this would be required. So this is equation 1 and this is equation 2. Okay. So now we have the height of the particle at point P and we have the velocity of the particle at this point is given by u square minus 2gh. Yes. So there is a tension along this direction. Yes. And mg cosine theta, the normal forces is acting opposite to the tension. So we have T minus mg cosine theta from the formula of free body diagram. Yes. T is acting along this direction and mg cosine theta is acting along this direction. Therefore, from Newton's third law, T minus mg cosine theta, this equals our centripetal force, that is mv square by r. Yes, because v square by r is the acceleration and times m, this is the centripetal force. Okay, so now this gives us T equals mg cosine theta plus mv square by r. So we obtain the force, I mean the tension force, or you can say the string force T as this equation. Okay, so let us name this as equation 3. Now we will discuss some condition that let's say what would be the condition so that the particle able to complete the whole circle, or if not, then
what is the condition so that the particles stop anywhere and fail to complete the whole circle? This type of questions we will now discuss. Okay, so starting with the first condition, let's mention this as case 1. We will discuss that implementing what condition the particle will able to complete the whole circle. We will now answer this question. Okay, so it means that the string does not slack. Yes, since the particle is completing the whole circle, it means that the string will not slack even at the highest point. Yes, because at this point the tension is minimum, right? So if it is not slacking at this point, it means the particle will able to complete the whole circle. Yes, so we are interested the tension in the highest point, that is at point B. Let's mention this as point B. So the condition is the string should not slack even at point B. Okay, so we need our T greater than equal 0 at B, right? This is the critical condition. Yes, now at position B the value of theta is pi, right? Yes, because this was our theta. Yes, so at highest position theta will be pi. So now if we now substitute the value at theta equals pi in our equation 3, we obtain T equals mg cosine pi plus m v square by r, right? Since t greater than equal 0, this implies mg cosine pi plus m v square by r greater than equal 0. This gives us m v square by r greater than equal mg. Yes, because cosine pi is -1. I just shift this expression in the right hand side. This gives us v square by r greater than equal g. This gives us v square greater than equal gr. So you obtain v square greater than equal gr. Okay, this is at the highest point at B. Now what does it mean? So if we now, let us now take the square root first. So v greater than equal square root of gr at B. So at the highest point the velocity should be greater than or equal. I mean, this should be minimum. V cannot be less than this quantity. If V is less than this quantity, then this will not hold, right? This condition will not hold. So at the highest position, the velocity of the particle should be at least this much. Only then the particle will able to complete the whole circle. Yes? Does it make sense? V mean, I mean the minimum velocity at the highest point should be at least square root of gr, right? So in order to achieve this velocity, so that the particle should able to complete the whole circle, or in other words, the tension should not be 0 at this point, or the string should not slack at the highest point, velocity of the particle at the highest point should be at least square root of gr, that is, should at least follow this v mean. Okay, so we will now substitute this v mean in equation number 2, which was our this equation, v square equals u square minus 2gh, right? We have determined this. So now what we are going to do, we will now substitute this value here, v mean square equals u square minus 2gh. Well, why we are interested in substituting the value here? Because let me tell you one thing, v is arbitrary, right? We do not know what is the value of v, because it is not the initial condition. Initially only u is given to us, right? We cannot say anything about v. V is changing at every point. Yes, following this equation, if h is changing, v will also change, because v is dependent upon h. But we know about u. So the motivation here is, what is the minimum initial velocity required so that this particle should be able to complete the whole circle. This is the motivation. We want to determine that, because u is in our hand, v is not in our hand. Yes, So by substituting this value here, we will able to get that minimum value of u, so that the particle will able to complete the whole circle. Yes? So we will write this u as u min, and our h will be 2r. Yes? Because in our highest point, at this point, h, this is 2r, right? Substituting the value of v min square here, gr, and from here we obtain our u min square as, it is just simplification, 5gr. This gives u min 5gr. Therefore, the initial velocity should be at least this. Therefore, the minimum initial velocity should be at least this much. Okay? Therefore, u greater than equal u min, in order the particle to complete the whole circle. Okay? Therefore, u should be greater than equal square root of 5gr, where r is the length of the string. Yes? Now we will go to our case 2, that when the particle, we write here, our case 2 will be condition for the particle leaving the circle. Okay? That is, the particle will not complete the entire circle. So definitely in this case u should be less than 5gr. Yes? Otherwise the particle will complete the entire cycle, as we have discussed earlier. So we obtain our right hand bound that u should be less than square root of 5gr. And what would be our left hand bound? We have to determine this condition. Okay. Since the particle is going to leave the circle, therefore the tension at the highest point, Tb, will be 0, right? Yes? At the highest point. Substituting this value in equation 3, what was our equation 3? T equals mg cosine theta plus mv square r. Yes, this was our equation 3. We will now substitute this value here. We obtain mg cosine theta plus mv square by r. This equals 0. This gives us, from here if we simplify, we obtain, and we also know this relation, right, from equation 2, that v square equals u square minus 2gh. So this gives us minus u square minus 2gh upon gr. This equals 2gh minus u square by gr. So we obtain our cosine theta as this expression. Okay? Yes? So far so good. If there is any doubt in understanding this, let me know. Yes? But it is very simple, isn't it, sir? Okay. So what we are going to do now, as I mentioned, we are interested in the condition of leaving the circle. So with this equation, I mean whatever expressions we have evaluated till now, we are going to determine that at which point the particle is going to leave the circle. Okay? Which point means at what height, what would be the height of the particle, so that at that height or at that point the particle is going to leave the circle. We are interested in the height. Yes? So from what condition the height will come? Yes, from equation 1 it will come, right? We have our equation 1 was something like this, right? That h equals r1 minus cosine theta. Yes? So now we are going to substitute this value here. R1 minus, we have our cosine theta is 2gh minus u square by gr, or you can write this in this way. I am just simplifying it, that's all. So you obtain our h as u square plus gr by 3g. So when the particle is at this altitude, okay, or at this height, say h1, at that point the particle is going to leave the circle. Yes? Or in other words, at that point or in this height, the tension in the string become 0. Yes? So far we are discussing about the tension of the string. So we came to this expression assuming the tension of the string is 0, right? Only then the particle is going to leave the circle. But what about the velocity of the particle? What will happen if the velocity of the particle becomes 0? Yes? So let's investigate that also. That is v equals 0. So if v equals 0, it means u square minus 2gh equals 0, right? From equation 2. Yes? This gives us h equals u square by 2g. Let's say this as h2. So we have obtained two equations of height, right? One is h1 and another is h2. From here we have at h1 the tension in the string becomes 0, yes? And from here at h2 the velocity of the particle becomes 0, yes? This one we obtain from tension equals 0 and this one we obtain from velocity equals 0. So can you ponder something from here? Let's discuss this one more. At h1 height the tension of the string is 0 and at h2 height the velocity of the particle will be 0. So when the tension is 0, velocity may not be 0, right? Because the particle was in a motion, correct? So after a certain period, once the particle get released from the tension, it will just leave the circle. That means it is still in some motion, correct? Therefore we can say that the height h1 is less than h2, yes? Because this thing will occur first. Once it occurs, only then it will occur. Correct? Did you understand what I am saying? When the tension is 0, the particle will just leave the circle. Since the particle is leaving the circle, it is still in some motion. It has some velocity. It does not mean that the velocity of the particle is 0. Yes, only the tension of the string is 0. So for that reason, the particle is just leaving the circle. And once the particle leaves the circle, after a certain period of time, the velocity of the particle will also be 0. So at h2 position, the velocity of the particle is going to be 0. Surely the h2 should be greater than h1 because this thing will occur before and after that this will occur. Yes? Okay, so from here we obtain u square plus gr by 3g less than u square by 2g. Yes? So if we now simplify this, I am just simplifying this, that's all. U square. See, we obtain the left hand bound of u. So u should be greater than this quantity and less than this quantity. Yes? Only then the particle will leave the circle. Yes? We will now discuss one more point, that the particle is neither completing the whole circle nor it's leaving the circle. That is, it is oscillating. Yes? Okay. So case 3. Clearly, since the particle is not leaving the circle, so when such situation will occur? Well, let me write it down. The particle, and if you have any doubts here, let me know, okay? The particle will oscillate. When it will oscillate? Only when the velocity of the particle, if the velocity of the particle becomes 0, but tension is not equal to 0. Yes? If v equals 0, but t is not equal to 0, the particle loses its velocity, but tension is still there. Yes, only this is the condition that the particle will oscillate in between 2 points. So when it is possible? See here, what we have did. In this case, the tension is becoming 0. Following that, velocity is becoming 0 after a certain period of time. But right now, what we have, the velocity is 0, but tension is not 0. So these situations will occur only when the inequality sign get inverse, right? That is h1 greater than h2. Yes? What is h1? The tension should be 0 And what is H2? How we occur at H1 when tension is 0, and how we occur at H2 when velocity is 0. But since in this case tension is not equal 0, but velocity is becoming 0, therefore H1 should be greater than H2, right? So we will just substitute the value of H1 and H2 here. U square plus GR by 3G greater than U square by 2G. Did you understand the logic? If you have any doubts, let me know, okay? It is very simple. If you now simplify this, this is 2GR greater than U square, and this gives us U less than square root of 2GR. Okay, so if U, I mean the initial velocity, our only business with about the initial velocity, as I mentioned, because we only know about U, that's all. So if the initial velocity satisfy this condition, then the particle will oscillate, okay? Okay, so now let us do some problem on this vertical circular motion, okay? Given a heavy particle hanging from a fixed point by a light, inextensible string of length L is projected horizontally with speed this much. Find the speed of the particle and the inclination of the string to the vertical at the instant of the motion when the tension in the string is equal to the weight of the particle. Okay, so let us first draw the free body diagram of the particle. So whenever you will get this type of problem, your first concern would be to draw the free body diagram of the particle. Okay, only then the things will become clear to you. You will get a clarity. Okay, so let's say this is theta. This is the lowest point. And say this is P. Here is M. As we have seen, this is mg cosine theta. This is our mg sine theta. Okay, and tension is around this direction. So let us first note down the data first, whatever is given in the problem. The length of the inextensible string is given is L, yes. Horizontal speed, that is U, acting along this direction is square root of GL, yes. Only these two conditions is given to us. Okay, so what we have to determine? We have to determine the speed of the particle, that is V. We have to determine V and the inclination of the string to the vertical at the instant of the motion when the tension in the string is equal to the weight of the particle. Note down this phrase, string is equal, tension in the string is equal to the weight of the particle. Okay, tension in the string is equal to the weight of the particle. That is when T equals mg, right? We need to determine theta when T equals mg. This is what it is being said here. Okay, we will come to that part later. First, let's determine the speed of the particle, that is V. So this is our first question. So we will solve this first. So as we have seen from equation 2 that V square equals U square minus 2GH, right? We can determine V from this equation, yes, because U is given as GL. U square is GL minus 2G, and we know H is R 1 minus cosine theta, yes. GL minus 2GL plus 2GL cosine theta. This gives us 2GL cosine theta minus GL. Okay, therefore we obtain our V as this. Okay, but we don't know about theta, right? So we have to determine our theta. Only then we can determine our V. Sorry, it will be V square. So for determining theta, we are going to apply equation 3, that is the tension equation. We have T minus mg cosine theta equals mv square by L, right? From here we obtain T equals mg cosine theta plus mv square by L, yes. But we are interested in t equals mg, right? Therefore, substituting t equals mg cosine theta. This is just now simplification. So see, these two equations, 1 and 2, we can equate this, right? Because these two are same. Therefore, 1, 2, this gives us 2gl cosine theta minus gl equals gl minus gl cosine theta. Simplifying, from here we obtain our cosine theta as 2 by 3, yes? So we have our cosine theta. If we substitute the value of cosine theta, from here we can obtain our v square, 2gl 2 times 2 by 3 minus gl. This gives us gl by 3. Therefore our v is square root of gl by 3, yes? So we obtain our v as square root of gl by 3